part of our lecture. Good, so the other point that I wanted to make before we dive in more fully to addition reactions to alkynes is when we start hydrating alkynes, which is coming up next, we're going to look at the reactions that add H2O across the one of the pi bonds in the alkyne. There's two types of intermediates you might or will run into. And I wanted to just get these on your radar screen now, because we're going to run into them in future chapters also. And I think it's going to be worth you guys knowing that these two types of structures are in general unstable and isomerize or dehydrate or something in order to form a more stable structure. Good, so this type of structure you might run into in this chapter, will certainly run into next semester. But you might run into it in this chapter also, depending on how you draw one of the mechanisms. And what you need to know is that a carbon with two OH groups on it, that is in general not a stable species. It's in equilibrium with a carbonyl compound. And the equilibrium nearly always very, very heavily favors the carbonyl compound. So the mechanism for going from here to here is one you're not responsible for yet. We will eventually learn it next semester. So what I've done instead is I've given you a step-by-step method to go from this geminal diol to the carbonyl. What you do is you pull off one of the OHs, and then you replace C single bond OH with C double bond O. That should give you an easy step-by-step, unambiguous way to get from this structure to this structure. I think you can see effectively it loses a molecule of water. This is essentially a hydrate. But these hydrates tend to be unstable, and so the carbonyl compound will be favored. So again, I think I've given you everything you need in order to get the right answer. What this means is that if you're answering a question and you come across, you draw a structure like this, you wind up with a structure like this, instead of get out of jail free, it's you get this structure for free. You can just put that structure next. And we'll do examples of all of this so you can see what we'll be doing. Again, we might or might not run into this in this chapter, but if you do in your travels, if you're writing a mechanism, let's say, and you see that you've drawn a compound with two OHs in the same carbon, then you can just go straight to this. You're not responsible for the mechanism yet. We'll get to that in, I think, chapter 19 next term, although it might be 20, but it's somewhere around in there. More to the point, still, this type of intermediate is known as an enol for obvious reasons, en for the double bond, ol for the OH. And what you need to know is that enols are by and large unstable beasts, and they readily isomerize to a compound that has a carbonyl, a C double bond O in it. And that's a special kind of isomerization known as a tautomerization. We'll have a lot more to say about that later. We'll define that fully later. And the mechanism, of course, we will get to later. So this also, you're not responsible for the mechanism yet. But it means that if you get to a structure like this, then you can just put down this structure next. You get that thrown in for free. And I've given you, once again, a step-by-step method to get from the enol to the corresponding keto form, as it's called. First, change the double bond, the carbon-carbon double bond to a single bond. Then, like you did before, replace C single bond OH with C double bond O. And then what you'll find is that there's a carbon that lacks an octet. So you attach a hydrogen to that carbon, which actually, you'll see we are O to hydrogen because we lose one from over here. So if you look at it, actually, those two structures are isomers. This is balanced for mass. So that step-by-step method should be all you need in order to get from an enol to the corresponding keto form. But in general, structures like this are much more stable. And we'll run into this really both with oxymercuration and hydroboration oxidation of alkynes. We'll run into this type of intermediate. We'll learn the mechanism of the tautomerization later, either later this term or next term. To be honest, I can't quite remember which, but we'll get to it later. Yes? You'll know whether you need to show the hours or not by how the question's phrased. but I'm showing, but the direction I've drawn is correct. In both cases, the equilibrium heavily favors those two carbonyl compounds. Good. Other questions then? I mean, well, I'll show you how this is applied and what you have to put down and so forth. We'll get to examples very shortly. This type of structure you'll run into if you use the book's mechanism for hydroboration, which I'm not recommending. I find it very strange, to be completely honest. But in that case, you'll run into a structure like this. But we'll certainly be running into enols in just a couple of minutes. Good, so I think that's all we need to say about that. Let me go to my whiteboard and we'll shut down the PowerPoint. And again, please be sure you register your attendance. I'm just doing 10 points for attendance today. So these are the reactions that I'd like to cover today. As I recall, we have both today and Friday to finish chapter 9. And yes, that's correct. We'll start chapter 11 on Monday. So I want to get through most of the remaining reactions of alkynes, at least the ones that are not special for alkynes. They're really reactions that we've learned already in the context of alkenes. And so the mechanisms we know already. So I'm not going to reteach them, but with one possible caveat here in the oxymercuration reaction. There's one bit of the mechanism that, to be honest, I don't really know, and I'll point it out. But other than that, the mechanisms are identical. So there's nothing new that you need to know in order to understand the mechanisms of the reactions. Just like with halogenation and hydrohalogenation of alkynes. You know those mechanisms already. We learned them in chapter 8. And that's going to be pretty much consistently true with the reactions we'll talk about today also, at least the ones that we know the mechanism for. We'll also talk about hydrogenation and oxidative cleavage or ozonolysis, and we didn't learn those mechanisms, and we sure won't here either. But with these hydration reactions, if you will, of alkynes, we know those mechanisms already. And so they're going to be exactly the same. Oxymercuration of alkynes comes into play because, according to your book, simple acid catalyzed hydration of alkynes is ineffective. That was news to me. That being said, I don't believe that's a reaction that I've ever tried. It just comes as a surprise. I would expect that it would work. But we'll take the authors at their word. I'm sure they've done their research. And so instead, we have these two reactions that cause hydration of alkynes to happen, just like they caused hydration of alkenes to happen. Recall that the definition of hydration means you're adding H2O across the pi bond. What that means is that one of the carbons gets an H, the other one gets an OH. And the only question is, are you going to get the Markovnikov product or the non-Markovnikov product? And that's going to be exactly the same for these two reactions as it was with alkenes. Oxymercuration gave us the Markovnikov alcohol with alkenes, with the added bonus that we didn't need to worry about carbocation rearrangements because there is no carbocation in the mechanism. And hydroboration oxidation, as its end result, gave us the non-Markovnikov alcohol, meaning not that the reaction is a rule breaker or an exception, but it's a natural consequence of the mechanism that the OH winds up on the less hindered, on the less hindered carbon, right? Because that's where the boron goes. So we already, in principle, know these mechanisms, so I'm not going to reteach them. That being said, your book launches into a whole different mechanism for hydroboration oxidation. I think it's very strange, but I'll get to that when we get to that in about 5 or 10 minutes. Let me just check our time here. Because I really don't see any need for you to learn an entirely new mechanism, and also it was news to me that you would get a different mechanism. Let me see. Are these reagents in excess? I think what you have here is fine. I think you'll need. I think actually you only need one equivalent of the mercury, but I would say in terms of what you see here, everything shown needs to be shown, anything not shown is okay not to show. I think the way you see it written here is fine. But one thing to be aware of is the reagents are a little different for alkynes than for alkenes with oxymercuration. We're not using mercury 2 acetate anymore. It's still a mercury 2 salt. So it's mercury 2 sulfate, just an aqueous sulfuric acid. That does bring up a point which actually I'm not entirely sure about, which is you'll notice there's no second step with borohydride ion, which begs the question, how do we lose the carbon-mercury bond? And honestly, I don't know. It's something I haven't taken the time to look into yet, to be quite honest. The first part of the mechanism is going to be the same, though. You're going to get the same as with alkenes. So if you need to review that, go back and look at the first part of the mechanism of oxymercuration of alkenes. You'll see that the Hg2 plus ion adds across the pi bond. It does that here too. You'll get a three-membered ring. Then you'll notice that we have a water molecule attacking at the more hindered position. The same thing will happen here. And eventually from that, you'll get something that looks like this, except instead of a carbon-hydrogen bond, you'll have a carbon-mercury bond. And how we get rid of that, I don't know. I'm hard-pressed to come up with a reasonable mechanism to convert the carbon-mercury bond to a carbon-hydrogen bond without a hydride reagent. So maybe I'll have to look into that. But certainly up to that point, we already know the mechanism. So I'm not going to reteach it. It's the same up till that point as here. After this point, to get to the hydrogen, I'm not entirely sure what the mechanism is. So I want to treat you like adults. I don't want to belabor that if it's something that I don't know, then if I don't know it, how can I ask you? I'd rather not belabor things like this. I want to treat you guys like the adults that you are. But in any case, we do get an enol, and it will be the Markovnikov enol, meaning that the OH will wind up on the more substituted carbon. And then we already went over our step-by-step method to go from the enol to the corresponding keto form. You will in any case wind up with a product that looks like this, that has a carbonyl in it. So I have some examples over here. But again, mechanism-wise, at least for the beginning of the reaction, the mechanism's the same. So you'll just put exactly what you would put with alkenes, and the wording of the question will make it clear what you need to do. But in any case, also besides, there's OWL questions that cover this, so that will give you some ideas. Not to mention my old exam. Anyways, the effect of the oxymercuration is going to be to give us the Markovnikov alcohol. With this particular starting material, of course, it doesn't matter, because that alkyne is symmetrical. Symmetrical alkynes are a good choice for this kind of reaction. We'll get to what happens if it's unsymmetrical. I just want to save that for the end. But symmetrical alkynes are a good choice because it doesn't matter which way you write the enol. It's the same thing. And once you go through your three-step method, you'll get the same compound. It doesn't matter if you put the carbonyl group over here or over here. It's the same compound. So what you need to know is that symmetrical alkynes are a good choice for this type of reaction. And there's only one possible compound. Doesn't matter which way you show it. There's only one possible compound. Of unsymmetrical alkenes, or unsymmetrical alkynes, there is one good choice, and that is when the alkyne is what we call a terminal alkyne. And the definition of a terminal alkyne is one that has an alkyne CH bond. It means the terminal, meaning the triple bond is at the end of the chain. So that's what the definition of a terminal alkyne is. It's an alkyne in which you have an alkyne CH bond. So that also turns out to be a good choice for this type of reaction because, again, with the same oxymercuration reagents, you'll get your enol at first. It will be the Markovnikov enol. And what that means is that the OH will wind up on the more substituted carbon, and I think you'll agree that carbon is a benzene ring on it, which is bigger than a hydrogen. So that's why I knew to put the OH over here and not over here. The OH will go to the carbon that's more heavily substituted. Make sense so far? Everyone remember talking about this with alkenes? Because with alkynes, it's exactly the same. Anyway, once you tautomerize this enol, you'll wind up with this compound. And that's a nice thing because terminal alkynes will always give you a methyl ketone. And if you want to memorize that sentence, that's fine. You can back up YouTube and watch me say it as many times as you like. I would rather you understood the reaction than memorized a sentence. But the point is that a terminal alkyne is a good choice for this reaction because there's only one possible product. Maybe it makes sense when the test comes up. Well, I don't know, it doesn't go smooth. Good, so what then if we used an unsymmetrical alkyne that was not terminal? That would not be a good choice for this reaction because you'd get two different products. You can see that over here with this one. Now it will matter where you put your carbonyl group. There'll be two different ketones. So that's not a good choice. You'd get a mixture. I wouldn't expect in real life we'd do a reaction like that. But symmetrical alkynes are good because then there's only one possible one. How do we know when the mechanism will follow Markovnikov's rule and when it won't? Well, we learned the mechanism back in chapter 8 that explained why it followed Markovnikov's rule. Because this comes from, the OH comes from water attacking the more substituted carbon. So that's how we know. It comes straight out of the mechanism. It's not that there's this external rule that's applied to the situation. But that mechanism is exactly the same for alkenes as for alkynes. Literally the same. You just put the triple bond exactly where the double bond was in the corresponding reaction that we learned in chapter 8. So the mechanism's identical. And the same thing's going to be true for hydroboration. There we'll see in just a moment that you're adding that BH bond across the alkyne, whereas before we added it across an alkene. Well, boron is bigger than hydrogen, so the boron's going to go where it has more space. And then later on, when you do the oxidation step, the carbon-boron bond gets converted to a carbon-oxygen bond. So that's going to be true here as well. The mechanism is identical, at least as far as I'm concerned. My point here with the alkynes is two good choices for this type of reaction are symmetrical alkynes and terminal alkynes. Anything that's not symmetrical and not terminal would not be a good choice. You would get a mixture of two compounds. And I don't think anyone would really do that in real life, because why would you want to get a mixture? At least I can't come up with a good reason. Good, but no, it's a good question. All of this comes straight out of the mechanism. If you know these mechanisms, then you don't even need to know the word Markovnikov, maybe, because all of these products fall straight out of the mechanisms. So like I said, I'm not going to reteach the mechanisms. Well, I might a little bit with hydroboration oxidation, just in order to make a point. But I'm certainly not going to reteach the entire mechanisms. But they explain everything. That's why it's important to know the mechanisms, at least when we can. And at least for the most part, for these two reactions, we can know the mechanisms. Good. So much for oxymercuration. Any questions on that at all before we move on to hydroboration oxidation? Yes. pH stands for phenyl, which is C6H5. It's a benzene ring with, well, do you see how there's a benzene ring with one thing on it? That's a phenyl group. You'll sometimes see pH used. You can also write C6H5, means the exact same thing. Totally fine. Or you can draw out the benzene ring. The thing to remember, as we said the other day with phenyl groups, if you've got a benzene ring with more than one hydrogen replaced with something, then you can't use pH. Then you have to draw the benzene ring out. So if there's 2 or 3 groups on the benzene, you have to draw it out. But for monosubstituted benzenes, pH is fine. Good. Other questions? All right. Well, let's clear these and we'll move on to hydroboration oxidation, which you can certainly also do for alkynes as for alkenes. And happily, now the reagents are exactly the same. And again, your book comes up with this different mechanism. It's news to me, and I actually know a little about hydroboration oxidation of alkynes because I did some of that in my PhD work. And it really is news to me. I don't know where they're getting it from. But the idea is the same. We'll start with an alkyne, and we'll treat this with typical hydroboration oxidation reagents. First step is borane THF, or if you want to use B2H6, that's also fine. And then the second step, remember, is alkaline hydrogen peroxide. And in the end, or at first at least, our intermediate that we'll get will be an enol. It will be the non-Markovnikov enol. Non-Markovnikov enol. And then that will rapidly tautomerize. I forgot something about a hydrogen. That will rapidly tautomerize to give us again a carbonyl compound. So same step-by-step method to get the right structure of the product. And we'll learn that mechanism later for tautomerization of an enol to form the corresponding keto compound. Good, but the mechanism is exactly the same. So again, a symmetrical alkyne is again a good choice of a starting material. And actually, if you think about it, if you've got a symmetrical alkyne, it doesn't matter if you use hydroboration oxidation or oxymercuration, you get the same thing. In any case, our first step is going to be treatment of the alkyne with borane THF. That's going to add a BH bond across the alkyne. And so at first, you'll get something that looks a bit like this, actually. And actually no wiggly lines here because, of course, the boron and hydrogen are going to add on the same side. So I think you'll get just this adduct at first. But then remember, there's two more BH bonds. And again, we covered this mechanism with alkenes. The mechanism's identical, the same arrows in the same places. So we've covered that mechanism already. But then you'll get a compound that has three of these groups attached to the boron. So it would look something like this. Here's our two ethyl groups. Here's our hydrogen. And there's our bond to boron. And so three of these attached to boron. That's going to be the next intermediate. If you're having trouble with the parentheses, you can also just draw it out. Some students have told me that they find it harder to understand with the parentheses. That's fine, you don't need to use the parentheses. You just make sure that you have two of the same groups attached. Let's see now. So either way, that's an ethyl group up there, though you'd never know it. No, don't clear. Can make that look a little better. Maybe something like that. Oh, question before. The definition of terminal alkyne is an alkyne is one that has an alkyne CH bond. So a CH bond where the C is triple bonded to another carbon. It's also called a terminal alkyne. You can think of terminal being as at the end of the chain. So you can write that intermediate either way. And then comes the oxidation step, which we learned that mechanism too. Alkaline hydrogen peroxide. Mechanism is identical. Same mechanism as before. And so what you get is, I think you'll remember how this works. You start with one of these alkynes, you get an intermediate that has three of those organic residues attached to the boron. And then after the oxidation step, you go, these three all become the same thing. And what you get by the mechanism, which again, we already know, it's the same exact mechanism, same exact arrows in the same exact places, but it's going to replace the boron with OH group. That's the end result of the mechanism. So please be sure that you still know the mechanism, but it's the same, exactly the same as with alkenes. And of course, that's an enol. that's going to be unstable, that's going to form a ketone that looks like this. I think I drew it like this before. 1, 2, 3, 4, 5, 6. I think I drew it like that. So you can draw it either way. Same thing. So bottom line, hydroboration oxidation of a symmetrical alkyne gives the same product as you get with oxymercuration of that same alkyne. Now, well, no, I want to stop here. Not stop entirely, but I just want to make sure I'll address the issue of what the book says on this in just a moment. Are there any other questions about this reaction? And again, just a reminder, the mechanism's the exact same thing as with alkenes. You don't have to know anything else. It's the same mechanism. The reason these compounds are in brackets is because they're intermediates. And you'll know by the phrasing of the question whether you need to draw brackets or not. But you'll often see in mechanisms, people put brackets around intermediates. Good. Other questions on this? Well, now the book is another idea about hydroboration of alkynes. And I do want to give another example too. I do want to talk about the terminal alkyne and what it would do. Your book is bringing up intermediates that have 2 borons in them. That is news to me. I don't think that would happen because once you attach 1 boron to this organic portion, that alkene is no longer electron rich. Remember, the boron atom is an electron poor atom, right? It only has 6 electrons around it. So I don't think that alkene is going to be too happy about adding to another boron. So, I mean, my understanding is that this mechanism is true. What the book says might also happen. I don't see any point to you guys learning a whole new mechanism when this one is certainly plausible and it's the same as what you learned before. So that's why I'm leaving it like this. I am not a fan of this 2 boron business. Now, if you did do it the book's way, I'll just finish this sentence and then I'll answer. If you do it the book's way, you'll still get the same answer. I just don't see the point of you learning a completely new mechanism. Yes? No, there's only one product because it doesn't matter where you put the CO, it's the same compound. See, that's why symmetrical, at least I hope it is. Yeah. Right, and not only that, but actually you get the same product as with oxymercuration. So it doesn't even matter which method you use if the alkyne is symmetrical. So but no, that's a good point. That's why a symmetrical alkyne is a good choice as a starting material. So now what can I do to show you that they're the same thing? Let's see. But they both have 6 carbons, and the carbonyl is on the 3rd carbon. This should prove it to you. So it doesn't matter which way you draw it. They're the same thing. And so that's why it's good to start with a symmetrical alkyne. What if we started with the terminal alkyne? What if we started with phenylacetylene? Well, we would get at first the BH2 compound. Wait a minute. Well, actually, this is now just CH2. It's pretty easy. Wait a minute. No, I'm losing my mind here. Indeed, I had it to begin with. BH2, right? The boron's going to go in the less hindered position because there's more room for it. And then that's going to happen twice more. 3 of these. Oh, we need a little more room though. Three of these. hydrogen here, and boron over here. So you get this intermediate. And oh, I should have put the reagents. This is the first step, BH3THF. And then this is our second step, aqueous alkaline hydrogen peroxide. Same mechanism as what we said before. You will get, again, an enol. Let me move the chat box. You just put the OH where the boron was, because that's what the mechanism determines, actually. And now if you do the three steps we did before, you'll get pH, CH2, CHO. You'll get an aldehyde. And that's another nice thing. Terminal alkynes give, why would the boron molecule not attach to the carbon with the benzene ring like before? Because the boron-hydrogen bond will add over here. I think you'll agree that BH2 is bigger than H, so it's going to go wherever it has the most space. So it's going to wind up over here on the less hindered carbon. That's what gives you the non-Markovnikov species at the end. So the reason that the boron goes on that carbon is because it's going to go wherever it is more room. It's going to go to the less hindered carbon. And the hydrogen is smaller, so it can go to the more hindered carbon. So yes, please do review this mechanism. But the mechanism is exactly the same for alkynes as for alkenes. Exactly identical. Same arrows in the same places. Does that help, though? Hopefully that answered that question. In any case, you're going to get an aldehyde out at the end. And that's another nice thing. So just as terminal alkynes, when we oxymercurated terminal alkynes, we can be confident of getting a methyl ketone. If you hydroborate terminal alkynes, then you will get an aldehyde. That's something we can be confident about. And again, I don't care really if you memorize those sentences, but it might be something helpful to stick in the back of your mind somewhere. But again, the mechanisms are absolutely identical. So in my remaining 6 minutes, if I may, I would like to cover hydrogenation of alkynes, which will not learn the mechanisms. We don't know the mechanisms. And I would also like to do, if we can fit it in, oxidative cleavage, which is ozonolysis. So please do review those mechanisms from chapter 8. They're the same as in chapter 9, and you will still need to know them. Good. Well, let's talk hydrogenation then. You will guess correctly that if you treated an alkyne with an excess of hydrogen gas using whatever catalyst, palladium on charcoal would be fine, well, you would expect to reduce the alkyne all the way down to an alkane. So it might say excess hydrogen, or it might say 2H2. You do need at least 2 mole equivalents of the hydrogen. But I'm sure you would all have guessed that. That makes perfect sense. Which immediately begs the question, what if you wanted to bring it down just to the alkene and no further? Can you do that? And the answer is yes, but now you have to worry, do you want the cis alkene or the trans alkene? We've got methods for both, neither of which you will need to know the mechanism for. If you want to get the cis alkene, then the reagent of choice, whether you put just H2 or excess H2 doesn't matter, because only one equivalent is going to add. You use something called Lindlar's catalyst. And this is something that contains palladium on charcoal, but they also add some other things like barium sulfate that reduce the reactivity of that catalyst. They call it a poisoned catalyst, which is kind of weird. But for that reason, it will add just one equivalent of hydrogen, and you will get the cis alkene and no further. It stops there. And you will only get the cis alkene. So we don't really understand the mechanism, but you will get the cis alkene. If you want to get the trans alkene, then your reagent of choice is lithium metal or sodium, doesn't really matter which, in liquid ammonia. And I'm going to have to comment on both of those. First of all, notice that this is the alkali metal. That's elemental lithium or sodium. And you can use either. So it's the actual metal. It's not the ion. And liquid ammonia means literally ammonia, which is a gas at room temperature, cooled down to the point where it condenses into a liquid. As I recall, it's around about minus 35, minus 40 degrees Celsius. So it's pretty cold. What you see in the supermarket is not liquid ammonia that's in those bottles. That's, of course, an aqueous solution of ammonia. By liquid ammonia, we mean liquid pure ammonia. And in that case, you will get only the transalkene, and it stops there. And you're not responsible for that mechanism either. So in the end, let's say that we used, again, since we happen to have it at hand, 3-hexyne. If you treated this with, actually, let me do it like this if I can. If you treated this with 2 equivalents or more of hydrogen gas, palladium on charcoal, you would just get hexane. 3, 4, 5, 6. Oh, pure ammonia will knock you out. Here, liquid ammonia is the solvent. For this, you can use a few different solvents. You'll get some ideas of what you can put there from OWL. I have seen acetic acid used, I've seen ethyl acetate used, but there's a few possibilities. If you treat this with hydrogen and Lindlar's catalyst, then you will get the transalkene. And if you treated this with lithium or sodium metal in liquid ammonia, then you will get the, ooh, I did that wrong. You didn't see that. Then you will get the transalkene. There we go. So simple as that. So, this is basically it for that. But yeah, so those are the reduction reactions of alkynes. You can get either the alkane or the cis-alkene or the transalkene. And the way you know which you get is by the reagents you used. Yes? We never learned it for hydrogenation. Well, I don't think anyone really knows what that mechanism is. I sure don't. So the way you need to know whether you need to know the mechanism or not is based on whether you needed to know it for chapter 8. One last quick one, and I have like a minute, but I think that will be enough. What about ozonolysis? You guys still have your scissors? I'll just use this alkyne as an example. Reagents are just ozone and dichloromethane. I don't believe you need the reductive workup with zinc and aqueous HCl or aqueous acetic acid. I don't think it makes any difference whether you include that or not. So for ozonolysis of an alkyne, you'll still start with your scissors. You'll cut your triple bond, but then your oxygen tweezers aren't going to be enough. I want you to take your Harry Potter magic wand and cast a carboxylic acid spell on both of those formerly alkene carbons. And that's what you'll get. So in this case, you'll only get one compound. So this carbon is those 2 alkene carbons. And since there's only one product in this case, you get 2 of the same. You only need to show it once, right? It's all the same. Yes. Right, it's symmetrical. If it were an unsymmetrical alkyne, then you'd get 2 and you'd need to show both. So, but other than that, it's very simple. Instead of scissors followed by oxygen tweezers, it's scissors followed by Harry Potter magic wand, and cast a carboxylic acid spell on both of those former alkyne carbons. That's a good place to end, especially since I'm out of time. Next time, we're going to start with some reactions that are peculiar just to alkynes, especially terminal alkynes. And we'll also enter the wild and woolly world of organic synthesis. Oh, question first before we end. Carboxylic acid. Yeah. Yeah, you cast a carboxylic acid spell. Good. Can you draw the last I just did. The last molecule's right here. Oh, do you mean you want to see the functional group drawn out? It's a carboxylic acid functional group. Good. So, well, we were clear in the last chapter, I think, about what knowing a reaction means in terms of whether you do or do not need to know the mechanism. So I've listed out what it means to know a reaction in chapter 8. And so you can apply that really to any future test. So I will see you all on Friday, and we'll continue and finish the chapter.